You're tuned in to Beyond the Known. It came from nowhere. No warning, no traceable origin, just a flicker in the data, moving too fast to belong to us. It didn't burn, it didn't hum, it didn't shine like a comet. It was silent, cold, precise, as if it had chosen its path long before our species even learned to look up. For 11 days, we watched it drift through our solar system, then it was gone. Some say it was a fragment of a long-dead world. Others, what if it was sent? Not as a message, but as a test to see who was watching. In this episode, we're going on a journey into the brief and pretty perplexing visit of Oumuamua. It was the first confirmed interstellar object to pass through our solar system.
And we're going to unpack what we actually know about her, how it was found, what it looked like, or what we think it looked like.
Exactly. And then we'll delve into the really strange behaviors, the things that just didn't fit the usual models.
Which led to some, let's say, creative theories.
Some quite controversial ones, yes. We'll touch on those. But finally, we'll anchor ourselves back in the latest scientific thinking, trying to explain this enigmatic wanderer.
Basically, we want to give you the clearest picture possible of one of the most intriguing cosmic mysteries recently. Let's begin with what we know for certain, the basic facts about Oumuamua.
Okay, so picture this. October 19, 2017, the Pan-STARRS 1 telescope, which sits way up on Maui's Haleakala volcano, it spots something. Now, this telescope is designed specifically to find really faint moving objects, things that are hard to see.
And this one definitely qualified as unusual pretty quickly.
Oh, yeah. Initially, it just got a standard designation, a 2017 U1. But it became clear very fast this wasn't your average asteroid or comet. So the International Astronomical Union, the IAU, stepped in. They officially named it ʻOumuamua.
And that I is important, isn't it?
Crucial. It stands for interstellar, making it the first confirmed object of its kind. They even created a whole new classification category just for it.
And the name itself, Oumuamua.
It's Hawaiian. It means something like a messenger from afar arriving first, which is, incredibly fitting. It really was our first confirmed piece of another star system visiting us.
A messenger carrying secrets. So it had been in our solar system for a while before we noticed it.
That's one of the kicker parts, yeah. We only spotted it in October 2017, but calculations show it probably crossed into our solar system way back around 1995.
20 years, just silently cruising through.
Pretty much, which meant by the time we saw it, it was already heading out. Its closest point to the sun, the perihelion, had happened over a month earlier on September 9th.
So we were trying to observe it on its way out the door, essentially.
Exactly. It did pass relatively close to Earth for a few months, about 0.2 astronomical units. That's roughly, 18, 19 million miles. Still a long way off for getting super detailed images. We were scrambling for data.
And its path, its trajectory, that was the dead giveaway it wasn't from around here.
Absolutely unmistakable. It followed what's called a hyperbolic trajectory. Its eccentricity was measured at 1.198.
Okay, break that down. Eccentricity.
So planets and most comets orbiting our sun have an eccentricity less than 1. That means they're in closed orbits, bound by the sun's gravity. An eccentricity of exactly 1 is a parabolic path just barely escaping. But 1.198, that's highly hyperbolic. It means Oumuamua was moving way too fast to be captured by the sun. It wasn't just visiting, it was blasting through.
Definitely not one of ours then.
No doubt about it. That high speed, that specific path, it screamed interstellar origin.
Okay, so we know where it came from, generally speaking, another star system. What about what it actually was? Physically, the shape was the first really strange thing people talked about.
It really was. The initial data, based on how its brightness varied, suggested something extremely elongated, like a cigar, maybe 10 times longer than it was wide, maybe 100 meters long, 10 meters wide, or even more extreme ratios were thrown around.
Which naturally fueled a lot of speculation.
It certainly did. But as scientists gathered more data and ran more sophisticated models analyzing its light curve, how its brightness changed as it tumbled, a different picture emerged.
Not a cigar.
Probably not. The later models suggested a thin disk or slab shape was statistically much more likely. Something like 91% probability compared to the cigar.
So like a pancake, a cosmic pancake.
Yeah, that's one way to put it. Maybe around 110 meters across, but only 16 to 19 meters thick. Very flat. Still really weird, just a different kind of weird.
And it was moving incredibly fast.
Unbelievably fast relative to the sun when it came to our system, about 26 kilometers per second. That's around 58,000 miles per hour.
Faster than our own probes, like Voyager.
Yeah, significantly faster than Voyager managed, even with gravity assists from planets.
Yeah.
Oumuamua just came in hot.
But relative to the local stars, it wasn't actually moving that fast.
That's the interesting part. Relative to the average motion of nearby stars, the local standard of rest at speed was much slower, only about 5 to 10 kilometers per second.
What does that tell us?
It suggests it wasn't violently ejected, like from a supernova or something. More likely, it was sort of gently nudged out of its home system and drifted through the galaxy for potentially a very, very long time before encountering us.
Okay, and what about its surface? Did it look shiny like metal or?
Not really, no.
Mm-hmm.
There were some early thoughts about changing colors, but more detailed analysis showed its reflectivity, its albedo, was about 0.1.
Meaning it reflected about 10% of the light hitting it.
Exactly, which is, well, it's pretty normal for space rocks. It's consistent with the reflectivity of many comets and asteroids in our own solar system. Sort of dark, maybe reddish, like dirty snow or rock, not like a polished spaceship hull or anything.
So fairly standard in a way. But its rotation wasn't standard at all?
Not even close. It wasn't spinning smoothly.
Yeah.
The observations showed it was tumbling chaotically, end over end, irregularly.
Like a badly thrown football, you said earlier.
Pretty much, yeah. And that made it really hard to pin down an exact rotation period. Different studies got different results. But the key takeaway was that it wasn't stabilized. No active control keeping it pointed in a certain direction, just tumbling.
So we have this fast-moving, oddly shaped tumbling object from another star. But despite gathering all this data, it quickly became clear that this object didn't follow the rules. We've established the basics of Oumuamua, a truly unique visitor. But what really launched it into astronomical legend and into the pages of science fiction were its baffling behaviors. Let's look at the specific oddities that made Oumuamua so unusual.
Right. The single most perplexing thing, the one that really got everyone scratching their heads, was its non-gravitational acceleration.
Meaning it wasn't just moving according to the sun's gravity, something else was pushing it.
Precisely. And this wasn't a small effect or some measurement error. It was detected with extremely high statistical certainty, a 30 sigma detection.
Which is incredibly certain, right? Like basically zero chance it was a fluke.
Vanishingly small chance. In particle physics, a 5 sigma result is considered a discovery. 30 sigma is just undeniable. It was real. As oumuamua was leaving the solar system, heading away from the sun, it got this gentle extra push outwards.
Like a rocket engine firing, but very gently.
Sort of, yeah.
Yeah.
The acceleration was mostly radial, directly away from the sun, and it got weaker as it got further away, roughly following an inverse square law, like gravity or light intensity.
Okay, but we see that kind of rocket effect with comets all the time, don't we? When ice turns to gas and jets out.
We do. That's the standard explanation for non-gravitational acceleration in comets. The problem was, Oumuamua showed absolutely no signs of being an active comet.
No tail, no fuzzy coma around it.
None whatsoever. And that's the second huge oddity. Despite this clear acceleration, there was no visible coma, no dust tail, nothing. Telescopes looked very carefully for the typical gases you'd expect from a comet, like carbon monoxide or cyanide.
And found nothing.
The limits were extremely low. Far too low to explain the amount of push it was getting. Same for dust. The amount of dust needed to create that acceleration just wasn't there. Orders of magnitude missing.
So it was accelerating like a comet, but looked like a dead rock.
Exactly. Which was incredibly puzzling, especially when you compare it to the second interstellar object we found, 2I Borisov, a couple of years later.
How did Borisov compare?
Borisov behaved exactly like a normal comet. It had a big, obvious coma and tail. It showed the expected outgassing. It fit the textbook perfectly, which just made Oumuamua look even weirder in comparison.
Okay, so no visible outgassing, yet it's accelerating. And then there was the tumbling motion, adding another layer of complexity.
Right. How do you get a steady push if the object is tumbling chaotically? Some research suggested the amount of torque needed to explain its weird tumble could be consistent with outgassing.
But wait, if outgassing was happening, wouldn't that spin it up like crazy?
That's the conundrum. If the outgassing came from one fixed spot, like a jet, the tumbling object should have spun faster and faster until it ripped itself apart. The physics demands it.
So how could it work?
The only way, theoretically, is if the source of the outgassing wasn't fixed, but maybe shifted around the surface, perhaps always staying near the point directly facing the sun, the subsolar point.
That sounds complicated and not typical for comets.
Not typical at all. It requires a very specific, unusual mechanism.
Yeah.
So the tumbling, combined with the acceleration and lack of a tail, just deepened the mystery.
And we mentioned its shape causing brightness variations. That was another piece of the puzzle.
Yes, the sheer amount of brightness variation was extreme. It suggested that very elongated or very flat shape, with aspect ratios maybe as high as 10 to 1.
The cigar or pancake again?
Right. And the way this light curve looked, broad peaks of brightness followed by sharp, narrow dips, strongly supported that idea. It implied we were seeing its broadside for a while, then very quickly seeing its thin edge as it tumbled.
But you said that was statistically unlikely to see so consistently.
Well, for us to happen to catch it, tumbling in just the right way, to produce such a dramatic, consistent light curve from our vantage point on Earth, it adds another layer of, let's say, statistical oddness to the whole encounter.
So scientists tried to explain the acceleration with known effects, right? Things other than outgassing.
Oh, absolutely. They went through the whole checklist, the Yarkovsky effect, it's heat radiating unevenly, way too weak, and probably pushing in the wrong direction anyway.
What about drag, friction from gas in space?
I would slow it down, not speed it up. So ruled out. Could it have been a collision? Some impact giving it a kick?
Did they see any evidence of that?
No. And the acceleration was smooth and continuous over weeks, not a sudden jump you'd expect from an impact. They also looked for things like an offset between its center of mass and its center of brightness. Couldn't explain it. Magnetic forces from the solar wind calculated to be thousands of times too weak.
Did they check if it maybe broke apart and we were just seeing one piece?
They looked, but no secondary objects or fragments were detected near it. It seemed to be a single intact object experiencing this mysterious push.
So after ruling out all these conventional explanations, the door seemed open for more unconventional ideas.
These unanswered questions, this cascade of anomalies that defied conventional understanding, naturally gave rise to some much more speculative ideas.
When the standard scientific playbook seemed to run out of answers, some researchers began to ask whether something more unconventional could explain these anomalies.
And that's where Professor Avi Loeb from Harvard entered the picture very prominently. He proposed something quite radical.
The alien probe idea.
Essentially, yes. He suggested ʻOumuamua might be, and I'm quoting loosely here, an operational probe sent intentionally by an alien civilization, or perhaps a piece of alien technology, like a solar sail.
A solar sail, like using sunlight for propulsion.
Exactly. A very thin, large surface designed to be pushed by photons from a star. Loeb pointed directly to that unexplained acceleration without a tail as prime evidence. He argued that a thin, lightweight structure would be pushed by sunlight in just this way.
And he drew a comparison to a human-made object, didn't he?
He did. He mentioned NASA's 2020 SO, which turned out to be an old Centaur rocket booster from the 1960s. It also showed slight acceleration from sunlight pressure because it was hollow and lightweight, and it didn't have a cometary tail. Loeb saw parallels.
So he was arguing that the natural explanations were just too contrived.
That was his position. He highlighted what he called half a dozen anomalies, and argued that explanations requiring brand new types of natural objects, things never seen before, had significant flaws. For him, the artificial explanation seemed paradoxically less strange given the evidence.
But that idea faced a lot of pushback from other scientists.
Oh, tremendous pushback. On multiple fronts. One major critique was motivation. Why send a probe on a fast flyby? It's incredibly inefficient for gathering data compared to an orbiter. And why fly by Earth but not get particularly close, never nearer than about 19 million miles?
The argument being that an advanced civilization would likely have better ways to observe us.
Precisely, like massive telescopes in their own system. Freeman Dyson pointed out long ago that interstellar travel is often more about why than how. The why for ʻOumuamua as a probe seemed weak to many.
And the travel time involved, that was another issue.
A huge one. At 26 kilometers per second, it would take at least 50,000 years to get here from the nearest star system, Proxima Centauri. From slightly further out, say 10 parsecs, you're looking at maybe 400,000 years.
Implying a civilization that's been around and planning this for an incredibly long time.
An almost inconceivable amount of time, far longer than human civilization has existed in any recognizable form. Plus, our own current tech, like Voyager, reaches comparable speeds. So it wasn't impossibly fast technology, just very patient technology, if it was artificial.
What about onboard instruments? Could it even observe effectively?
Well, given its size, maybe 100 meters or so, any telescope on board would be limited, maybe 10 meters aperture, that's good, but vastly inferior to what an advanced civilization could likely build as a large interferometric array in space back home to study Earth in detail over millennia. The flyby seemed primitive by comparison.
And the tumbling, how did that fit with the solar sail idea?
It didn't, really. A functional solar sail needs to maintain a specific orientation to the sun to get a consistent push. It needs attitude control. Tumbling randomly would make the push incredibly variable, not the smooth acceleration observed. It would suggest the sail, if it was one, was derelict and uncontrolled.
Like space junk.
Exactly, which leads to another problem. Loeb also claimed it was unusually shiny, like a sail should be.
But the data didn't support that.
No, as we said, the albedo was measured around 0.1, consistent with dark asteroids or comets, not a reflective mirror-like sail.
And if it was derelict alien space junk,
Then the statistics become mind-boggling. Based on detecting one oumuamua, estimates suggest there could be something like 124 but 1,025 similar objects drifting through the Milky Way.
an unbelievable amount of trash.
Just an astronomically huge number. The idea that a civilization or many civilizations would litter the galaxy with that much debris seems highly improbable to most scientists. So Occam's razor, the simplest explanation, still favored a natural, if unusual, origin.
Okay, so the alien probe idea, while headline grabbing, faced serious scientific hurdles. What about other unconventional natural explanations? The hydrogen iceberg.
Right, that was proposed by Seligman and Bergner. The idea is that cosmic rays hitting water ice over millions of years could create and trap molecular hydrogen, H gas, inside the ice structure.
Like tiny gas pockets.
Exactly. Then as Oumuamua got closer to the sun and warmed up just a little bit, this trapped hydrogen could sublimate, could leak out, providing thrust.
And because it's hydrogen gas, it would be invisible. No tail.
Correct. Hydrogen is very hard to detect directly, and it wouldn't necessarily release dust, so it could explain the acceleration without a visible coma. They calculated the required mass loss rate was plausible, maybe 10 to 800 grams per second.
But there was a catch.
The catch is whether hydrogen ice or water ice with trapped hydrogen could actually survive for potentially millions or billions of years in interstellar space. Some research suggests H2 ice is quite fragile and might be destroyed by cosmic rays or sublimation over those timescales, so its longevity is a question mark.
Then there was the nitrogen iceberg theory, a chunk of an alien Pluto.
Proposed by Dish and Jackson, yeah. They suggested Oumuamua could be a fragment knockoff of Pluto-like icy dwarf planet in another solar system, made mostly of solid nitrogen, N2.
Like we see on Pluto and Triton in our own system.
Exactly. Nitrogen ice can be very pure. As it neared our sun, the N2 would sublimate, providing the rocket effect. And because it's pure, there'd be very little dust to create a visible tail.
And they estimated how much mass it might have lost.
They did. Their models suggested it might have lost as much as 95% of its original mass just during its passage through our solar system since 1995. They also argued that such fragments could be relatively common, maybe making up a few percent of all interstellar objects.
Plausible, then.
It's considered a strong contender. It explains several anomalies quite neatly.
And the last one? The cosmic dust bunny.
Proposed by Jane Liu and others, this suggests Oumuamua wasn't a solid object in the traditional sense, but an extremely porous, low-density aggregate of cosmic dust. Think incredibly fluffy.
How low density are we talking?
Maybe thousands of times less dense than water, barely holding together.
How would that explain the acceleration?
If it's that light and fluffy, even a tiny push from sunlight pressure or very minimal outgassing would be enough to cause the observed acceleration, and its fragile, porous nature might explain why no significant dust was seen. There wasn't much solid stuff to shed.
So 3 very different, quite exotic natural explanations. Hydrogen ice, nitrogen ice, or giant fluff ball.
Each trying to tackle those core mysteries. The push, the lack of a tail, the shape, the tumbling. It really shows how Oumuamua forced scientists to expand their thinking about what sorts of natural objects might be drifting between the stars.
But before accepting the extraordinary, even these exotic natural ideas, the scientific community returned to more grounded possibilities, rigorously testing them against the data. As with every episode, we entertain the possibilities, but if you're familiar with our episodes, this is the part where we return to the data. This is where the science has its say.
And despite all the speculation, the explanation that still holds the most weight within the scientific community comes back to a more refined version of cometary activity, specifically outgassing, but perhaps involving hydrogen.
So back to the hydrogen idea, but maybe linked more closely to regular water ice.
Kind of. The thinking is that Oumuamua is likely made mostly of water ice, like many comets. But during its incredibly long journey through interstellar space, it was constantly bombarded by cosmic rays.
We talked about that breaking down water.
Exactly. Breaking H2O into hydrogen and oxygen. The hydrogen atoms can then get trapped within the disordered amorphous structure of the ice. Billions of years of this process could build up a significant reservoir of trapped H2 gas.
And when it neared our sun?
The slight warming, even if not enough to make the water ice visibly sublimate and form a tail, could be enough to cause the ice structure to rearrange slightly, releasing the trapped hydrogen.
Giving it that invisible push.
Precisely. An invisible push from hydrogen gas escaping, which wouldn't necessarily carry much dust with it, explaining the lack of a coma or tail. The required mass loss, 10 to 800 grams per second, is plausible and matches the observed acceleration.
Does this happen with comets in our own solar system?
It's thought to be particularly relevant for objects that spend a long time in the outer solar system or the Oort cloud, where they're exposed to more cosmic rays outside the sun's protective heliosphere. So yes, it's a known process, just perhaps more extreme in an interstellar visitor.
And this hydrogen release could also explain the tumbling.
It could. The release of gas creates thermal recoil forces. If this release wasn't perfectly uniform across the surface, maybe happening in bursts from different spots as different parts warmed up, it would create uneven forces and torques. The amount of torque generated this way seems consistent with what's needed to explain Oumuamua's chaotic spin, similar to how outgassing affects the rotation of comets we observe regularly. So it potentially ties the acceleration and the tumbling together quite neatly.
Okay, so that covers the weird behavior. What about the weird shape? The pancake or cigar? Is there a natural way to get that?
There is, and it's considered quite compelling. Tidal fragmentation.
Meaning it got ripped apart by gravity somewhere?
Exactly. The idea is Oumuamua isn't a whole object formed that way, but a fragment torn off a larger parent body, maybe an icy planetesimal or a comet, when it passed too close to a massive object in its original star system. Could be a giant planet. Could even be the star itself.
Like stretching taffy, but with a space rock.
A pretty violent version of it, yeah. The immense gravitational forces would stretch and rip the parent body apart. And simulations show this process naturally produces elongated or flattened fragments, just like the shapes proposed for Oumuamua.
And these fragments would get ejected into interstellar space?
Yes, often at high speeds. This could happen during planetary system formation, or later collisions or close gravitational encounters. Events like this and the Kuiper belts of other solar systems could be constantly seeding the galaxy with icy debris.
Is this common enough to explain finding Oumuamua?
The models suggest yes. While early estimates of interstellar comets were lower, when you factor in fragments from tidal disruption events, especially involving icy bodies like exoplutos, the numbers go up significantly. Some models predict maybe 3% of interstellar objects could be Oumuamua-like fragments from these events. So statistically, it starts to look less like a complete one-off.
And again, comparing it to Tua Borisov really helps frame this, doesn't it?
Absolutely. Borisov looked and acted like a conventional comet. It had the tail, the coma, the expected composition. It showed us what a normal interstellar comet probably looks like.
So Borisov was the baseline, and Oumuamua was the outlier that needed explaining.
Precisely. Borisov confirmed our basic understanding, while Oumuamua forced us to consider these more complex or extreme natural processes, like hydrogen outgassing or tidal fragmentation, to explain its unique properties.
And the key to really figuring this out is finding more of them.
Without a doubt, we need more data points. And the good news is we're about to enter an era where we should find many more.
You mentioned the Vera Rubin Observatory.
Yes, VRO. It's an 8.4-meter telescope designed for massive sky surveys. It's expected to find potentially dozens, maybe even up to 100 interstellar objects per year once it's fully operational.
That's a game changer, from 1 or 2 to potentially hundreds.
A complete game changer. And alongside it, NASA's Near-Earth Object Surveyor mission will use infrared, which helps determine size more accurately, regardless of how reflective the object is.
So we'll get a much better sense of the population, how many there are, what shapes and sizes they come in, what they're made of.
Exactly. Current estimates guess there might be thousands of these objects passing through our solar system at any given time, most too far away to see. With VRO and NEO Surveyor, we'll start building a real catalog, a real understanding of these visitors from other stars. We'll see if Oumuamua was truly bizarre or just the first example of a common, albeit strange, type of object. It left our system as quietly as it arrived, no signal, no answers, only questions trailing in its wake. And as it vanishes into the dark between stars, we're left to wonder, was it the first of its kind, or simply the first we noticed? What mysteries do the next interstellar visitors hold? That's it for this journey beyond the known. If the unknown speaks to you, liking, subscribing, and following truly helps us grow during these early days of the channel. And if you're ready to go even deeper, consider becoming a member for Vault Access or Secret Passage, where early episodes, the audiobook Underground, and hand-curated wonders await.